So, hi everyone. Thank you for joining today. My name is Jason Key at SBGrid in Boston, Massachusetts. This is our SBGrid webinar series. The webinar series is open to everybody and not just an SBGrid centric thing. So check out our schedule. It's online. Share it with anybody that you think would be interested. Again, open to everybody. And thank you for joining. We record most of these unless in some cases, if people don't want them to record them, we don't. So, but most of these are on our SBGrid TV channel, so you can catch those. And that's particularly good for people who are in the sort of later time zones. So on that note, Paul, thank you for sticking around late and agreeing to give a presentation today. I think we're all excited to hear what's new in Coot. So
well, I didn't notice I didn't give you a title, but that is exactly what my title is.
yeah, I feel like that could just be the standing title for.
Well, it has been for the last 15 years. Okay, I'm going to start. So do you want to transfer the screen to me?
Yep, you should be able to just share your screen and take control.
Oh, okay. Share screen and continue.
All right, go right ahead.
Right. Okay, so let's get started. So you have given me 40 minutes. So my aim is to finish at around 1:45. Now, I read your instructions to the authors, and hopefully I'll abide by them, except for one, which was the number of slides which you recommended to be 20. I have about 60. So I hope that won't be too much of a problem. Many of them are screenshots and won't be too intellectually challenging. So Coot is programmed for macromolecular model building, refinement, validation, and as I hope to show you, now representation. So this presentation will be in two parts, and I'll be discussing 0.9 series in the first part and the 1.0 series in the second. So what's new as a consequence of 0.9 is changes to the fitting, the contouring, and in particular real space refinement in part 2. As in the pipeline work, code that I'm writing routinely, probably for most of the last 2 years, and that's in GitHub, and it is what will become Coot 1.0. More on that in part 2. So part 1, what's available today? If you wanted to download a Coot binary, what would you get? You'd get 0.9, and the big change in 0.9 for me, I suppose, was that I moved to a new dialect of C++, C++11, which is a big change in the language, changed the way I program, and allowed the use of threads. And so the use of lambda functions and threads changed the way I programmed Coot. And I've been bringing that thinking into all of the aspects of the functions that I'm developing since I've learned how to use it. And it took a long time to learn. So this has been in development since 2016, I think, maybe late 2015. And I've been learning how to use this version and how to use threads. Because Coot wasn't designed to use threads when it first was written a number of years ago now. And so I have had to delete the old thinking in order to bring threaded thinking into these aspects. So threads have been added to, or have been reworked to optimize, which is to say speed up the representation of rotamers and dynamic interaction dots or clashes. The map has been improved, both the contouring and the reading. Jiggle fit, which is local molecular replacement, which is a very useful tool. I find it a very useful tool in cryo-EM reconstructions. Very frequently, we want to be doing model building by adding terminal residues, and the ability to look ahead, refine, score, and then prune gives far more robust results. And as a consequence of that, being multiple threaded, we can cover more fly size space as we test the hypothesis. But it is in real space refinement where the threading is most apparent, or the usefulness is apparent on a day-to-day basis. I'll come back to that in a moment. We also have Ramchandra plot updates, curlew, sequence view, and ligand search. So I will talk about the real space refinement first. No, I won't. After this slide. I mentioned that the maps have been improved. So I had been using the CSP4 libraries for reading cryo-EM reconstructions, and that read the maps slice by slice. So you might have 200 different slices, or even more in some cases. And each of those was a new function call that allocated memory from the operating system. And that took some time. Now, Coot calculates or asks, queries the size of the file, and then allocates that amount of memory and does it once. So one memory allocation, one call to read. Then it has to be converted from a file representation into the internal representation. Coot uses Clipper, and that's done in a multi-threaded fashion. And so the reading of maps is just invisible now, except for the very largest reconstructions. Everything is practically instantaneous. The contouring has been improved, so that is multiple threaded. So the sections are split into sets of sections, and each of those gets sent off to its own core on your workstation. There's a new mode called No Auto Recontour mode for cryo-EM reconstructions again. What that does is, by its name, it stops Coot contouring the map after you've moved the center. So very typically, the way you'd use this is to recontour or contour initially the whole of the reconstruction, and then turn off recontouring so that wherever you move, the contouring remains. And because you've recontoured the whole of the reconstruction, it's just there, and it's just instantaneously there. So I find that useful, and I'm looking more at membrane proteins these days than ribosomes, so it may not work so well for ribosomes, but for most reconstructions, I think that'll be a useful mode. Right, as I said, the major place where the threading is apparent is in the real space refinement, and in particular the real space refinement of into low resolution maps, or using low resolution information to do large scale motions. So let me introduce the concept of Gemin-McClure restraints. These are, well, I use them synonymously with local distance restraints, Gemin-McClure restraints. And the idea in this case is to use a high resolution reference structure and use the local environments there to inform the refinement of today's structure, which is the APO form. It doesn't have the ligand bound, it's lower resolution, more flexible. And so we want to bring information from that high resolution structure to the refinement of this molecule here. So what we do is, if I do a superposition, you can see they're similar. But there is some systematic shift of the domains around the binding pocket. We ask the question, for every atom in the reference structure, what are your neighbors? And we can say neighbors consist of those that are within 5 angstrom. And then given this set of neighbors, what are the distance to these neighbors? And then we can ask that for every atom. That gives us a set of local distance reference distances. And then the idea is to apply those reference distances to our current model. But because they're local, they allow large-scale motions while encouraging local environment changes to be minimized. We can represent that like this. So where the reference distance matches the distance in our current model, the color is gray. And where in our current model, the distance is longer than the reference, it's red. And vice versa, blue. So it's no surprise that around the binding pocket of a ligand binding protein, where the ligand is not present, then the two domains have drifted apart a bit. So that's what we're seeing here. The color red in Coot is typically used to mean error. That's not what I'm trying to represent here. So I've changed the color scheme to green to purple, which is less less problematic. You don't look at the color red and think, oh, that's a problem. So it's just longer or shorter than the reference, and it's not wrong that it's longer or shorter. It's just useful information. And as you progress with the refinement, these colors dynamically change. Right. So very typically, we use Hooke's law in the generation of the formulation of the target function, the penalty function. So if we have a distance, let's say, and we move, I'm going to try to represent that here. So if we move a little way, if I put my cursor on the screen, can you see that? No. Okay. So the idea is we move between those two pale blue lines, and as a consequence of doing so, then we get to change the penalty that we pay for the atom being in that new position. So using least squares, you can see the top rectangle. This is quite a substantial increase in the penalty score as a consequence of moving the atom in that way. Using the Gemin-McClure M estimator, which is modified the target function, it allows or reduces the price we pay in terms of contribution to the penalty function for the same movement. And as you can see, as we move further away from the equilibrium position, we get less and less increase from the Gemin-McClure and more increase from these squares. So that changes the way, it changes the form of the function and allows large scale changes. And this is a number that we can tweak to optimize the way we get to move the molecule. And often when I'm doing this sort of modeling, I can see that the restraints are too strong. So there's a menu item on the menu that allows you to change the weight. And so it can be adjusted either to improve it or to increase the weight or reduce the weight, depends on how the model's behaving. Very often the case, though, that we have a homologue, and at the start of our modeling, the homologue is the reference, or the current model is the reference model. So these are self-restraints, and they don't need sophisticated model interrogation to determine a self-restraint. They can be calculated internally and added to the refinement. So the idea is to add extra information into the refinement that says keep the local environment similar to how they were when you started, but allow large-scale motions because the weight is adjustable. In Coot, we are using a first-order derivative-based method, unlike RefMac, which is second-order based method. And there is a technique called jelly body in RefMac to address this the same sort of problem. But that technique can't be used in Coot because that uses a modification of the second-order derivative, and Coot doesn't have those in its formulation of the gradients. Right. So the Coot tutorial has been updated in the last, well, I continually tinker with it, but this is its current state. So we have a structure that was from the lab of Laurie Passmore, my colleagues from a year or two ago now. What we're trying to do is fit this beta propeller WD-40 domain, and we have a homologue. So the idea is to beam in the homologue and place the middle of the model of the homologue onto the middle of the particle and do this local real space refinement, the local molecular replacement. It's called jiggle fit. And that gives us a orientation of the model there where this domain doesn't quite fit. So then we can take this domain and do a jiggle fit of this. And we get a better fit. But we want to further improve it, and let's not forget that this is the homologue sequence, not our sequence. So what we're going to do is strip off the side chains. It's 20% sequence similarity, identity in this case, and generate these local distance restraints. And using the default weights, it seems the reasonable functional form and scaling to the standard restraints and fits the density to make these usefully move the atoms in a substantial way to fit the density. In fact, the video from 2019 has, well, okay, it's the previous iteration of this, but largely the current situation is as it is in that 2019 video, if you wish to look at it. Okay, and having done the refinement, it takes a few seconds. Well, I say a few seconds, it's more like 30 than 3. Then we get a better fit. And if we zoom into one particular fraction here, this is the worst fitting part. So this was pre-respace refinement, and then we turn on these local distance restraints and have it refine into density. And consequently, we come up with a reconstruction or a fit to the reconstruction that looks like this. And as I said, this is the homologue. So the sequence of the homologue doesn't match what's in the reconstruction. So we need to do some adjustments and sequence alignment and modification of the side chains and some pruning of some residues in order to get the correct sequence. But that's not part of real space refinement and doesn't use threading. Not today. All right, what else do we have in 0.9.x? So what's been improved is the Ramchandra plots. So this update has been improved not by any of my work, but by those of others. So Andrea Thorne and her team have taken the top 8,000 structures from the Richardsons and done the sampling of that and represented that as a high resolution, more tightly, the residue type is more accurate. And we have a number of Ramchandra plots for different residue types now. And so now all these have been encoded up into Clipper by Andrea, and then from Clipper to Coot by Bernard. And so if you see new Ramchandra plots, it's a consequence of their work. Right, what else do we have? We have Curlew, which is the way in which I can give you access to interesting scripts. So if I make a mistake in the scripting API, then I can install or quickly add an extension. That's what Curlew stands for, by the way. The Coot Utility Refinement Library Extension Wrangler. I can add an extension that you can quickly download, click, it's done, you're updated. And it doesn't take the time and the weight that a real full update does. More recently still, the ligand search now can take the MMSIF description of ligands and turn them into chemical diagram, which is something I've wanted to do for quite some time, and at last we have it. So you click, you do your search, you get your search hits on the list, then you click on the list on the right, and then it imports it into the graphics view on the left. I hope that will be of some convenience. So it turned out to me, without going into too much detail, that Coot was not used by Coot users, especially more recent PhD students, in the way that I expected them to use it, and they were quite resistant. So having thought about that, reflecting on it, I am now changing the program to act in a way that's expected rather than in a way that I thought was a good idea in 2004. So one of those ways is to bring all of the functionality into one frame instead of multiple floating dialogues floating around the screen. Coot will bring its information into this panel, into this frame here. And the first tool that's been embedded here is that the sequence views have been embedded. Now, if you look closely, you can see that at residue 49, there's a highlight in the sequence view, and this is the residue we're currently centered on. if I press the space bar now, then it would move to residue 50, and the highlighted residue, the little orange box, would move on to residue 50. So it's interactive, and of course, as it was before, if you click on the sequence, then you move to the model. So it's both way around. All right. Now, it would be a nice idea to have validation markup on that sequence view as well. So we could add secondary structure, validation, make it all clickable, but that's not there today. Right, something that I've been resisting for a long time, 10 years, was using a bond orders in the protein. I didn't think it would be useful, but having implemented it and lived with it for a couple of months, I rather like it. So there's a nice hydrophobic pocket in a protein. I think it's apoferritin, but I'm not sure. Right, and yes, and you can see that it's taken an aromatic description of the, well, it's taken the A-strug representation of the amino acids and used the bond orders there to represent the chemistry. And I think it looks nice now. I didn't think it would, but there we go. I hope you find it useful. It can be found in the color by chain option in the display manager. Right, so we're halfway through, and much of the rest of the presentation is going to be screenshots and eye candy and not intellectually challenging. Right, so Coot 1.0. So this is what, as I have said, what I've been spending most of the last 2 years on, and I'm enthusiastic about it, and that's why I'm telling you about it now, even though the binaries are not readily available. Right, so it used to be the case that Coot represented the structure with 3D colored sticks in space, merely ambiently colored sticks in space, using a graphic system or library from the 1990s, maybe even earlier than that with IRSGL. No use of lighting. 2 months it took me to learn it and implement the representation, and it has changed little since then. Now, as you may know, Python has updated and Python 2 has gone away. It's time to move to Python 3, and as a consequence, I need to change the GUI, which is GTK, and the graphics, which is OpenGL, as a consequence of changing the Python version. And both of the first two there have taken a couple of weeks each to do the update, which was time consuming enough. But the OpenGL has taken me, well, more than a year, more than a year's work of trying to work out how to make it work. Every pixel has to be rewritten from scratch. I had no knowledge of making graphics work with modern graphics infrastructure or graphics library infrastructure and how it works with the hardware. So I had to go back to school and, as it were, go to Graphics Programming 101. And it turns out that every single tutorial and book dedicated to OpenGL presumes that the developer is trying to program a game. So in order to learn what it was that these tutorials are trying to teach me, I've been infused with game developer thinking, as you'll see. But first of all, lighting. Flat ambient shading, the way it currently works, makes it difficult to perceive depth, as we'll see in the next couple of slides. Modern hardware allows the use of sophisticated lighting systems to make the perception of depth and the juxtaposition and configuration of the scene more readily apparent, so that perhaps the need for stereo will be less strong. So the lighting system that I'm using in Coot is today ambient diffuse, specular, ambient occlusion, and Fresnel. They're all programmed from scratch by me, and I must say that I have from time to time fired up Chimera X, and I've been comparing and contrasting Coot with Chimera X. They do such a good job. It looks gorgeous, and Coot doesn't look as gorgeous as Chimera X does. The ambient occlusion brings something to the party in Coot, but it's better in Chimera X. I often shake my head and wonder how they did it so quickly and so beautifully. Also, shadows in Chimera X also improve the representation, and they're not at all represented in Coot. Maybe some things for the future. So I've got some screenshots of how new Coot is an improvement in than over old Coot. At least I hope to show you that that is the case. So when we're zoomed in, the lack of depth really is not so terrible. We can see where the map is, we can see where the model is, we can see what's in the background, we can see above, beyond, and below. It's not too terrible. And when we're working with average resolution or better resolution maps, it's not a bad representation. But using Coot for cryo-EM reconstructions, it is this sort of representation just is not that useful. So very typically, we look at the whole reconstruction, and if you do that in Coot, using old Coot, you get little out of it. It's just a monochrome Rorschach plot. So that's not helpful, and we'll be coming back to this. And also, very frequently, when my colleagues are looking at reconstructions, they're doing it against a white background rather than the typical black background that one uses in Coot. So I've tried to take that on board too and adjust the lighting system so that it works well on a white background. So some Coot 1.0 screenshots. So this is a typical view of 1.0. This is taken from the tutorial with the ligand on the right and the flipped sidechain on the bottom left at the 7 o'clock position. I've tried to make it so that it's quite similar to the old way. So at least as you start off, it's not too substantial change in style of representation. So the model is represented as shiny plastic. So if you look closely, you can see that it's got a material property as if it were made of something like Lego, tubes of Lego. The density looks like wool, especially when you zoom out. But the idea was to keep the sort of view where we're looking at the residue scale similar to how it used to be in the old version, because it wasn't too bad a representation. What's changed here is that you can manipulate this in a number of ways. So, for example, you could change the transparency of the lines here, which one was not able to do in old Coot. So as well as the maps and models, there's also the validation markup that's needed to be represented. And here I'm representing, as you can see, various degrees of discomfort of these these pink sticks or tubes or pills. They're representing a clash, whereas before we represented a clash with a pink stick. Here we have a pink tube. And that looks rather appealing, and it's also interactive as well. So as I'm moving the atoms around, the atoms clash gets updated because, as I said, it's now calculated with threads. So additionally, again, Coot is now able to represent ribbons, represent macromolecules as ribbons. It's not fully featured, so things for RNA and DNA don't have all the ladder styles that one might see before MG, I should say. Thanks to Martin Noble, who's provided this library to me. I've just included it into Coot. And that works at full speed. You can take ribosomes with ambient occlusion and do full ribbon representation, and it rotates at 60 frames per second. It's impressive. Right, so we saw this picture before on a black background. but so this is old Coot again representing that map. So let's take this same map and represent it with the new version of Coot. Can we get a more useful representation? And I would argue that we can. What I've done here is change the representation style to solid surface, and the ambient occlusion really adds something to the interpretability of the map. If we did a side-by-side of this, we could see that it's quite close to Chimera, but I think most people would, Chimera X, would, including myself, especially with a number of structures, give the tick to Chimera X in terms of interpretability due to ambient occlusion. But this is not bad, and a certain improvement over where we used to be. So I mentioned that we can change the material properties, and here's a piece of DNA. I've turned, well, obviously the resolution's higher, and you can see that it's got some specularity here, so it's kind of shiny, so sort of shiny wax effect by changing the material properties. What else do we have? We can do 3-point studio lighting. So there's a big light at the back of the scene and 2 smaller lights at the front. And the way that lighting works is that it brings out the structure of the map by highlighting the edges of the map. And this works nicely interactively. This is a screenshot, obviously. You lose something in screenshots. Additionally, in this representation, you can see I blurred out the background, and that also brings something to the representation and interpretability. This is an in the clinic anti-cancer ERK1 inhibitor, by the way. Again, using Coot for representation of the map. So this is sapphires and emeralds. But no rubies. So I've taken just the positive level of the difference map here, and we are looking at a map that's been calculated without hydrogens being in the model. And this is an FOFC map, and you can see density that this particular part of the structure illustrates a hydrogen bond network, including a water. That's at the middle of the screen there, slightly to the top right at the 2 o'clock position. So using difference maps in cryo-EM reconstructions, I think, is going to be routine. It currently isn't for me or my colleagues, but I think within a few months or a year or so, it will be routine because it brings a lot of value with little cost, especially now that we can do them updatingly. So Kathy Lawson and colleagues recently announced the cryo-EM modeling challenge, and this is one of those structures for which we need to look at the ligand environment, but I just happen to be looking at other parts of the structure with this difference map. And you can see here, obviously, that the formally charged side chains, the acid side chains, and maybe even that argin out there, are covered with red density. What that means is there's more calculated density there than observed. And it might be that the scattering factors are wrong here, but it might also be that those atoms are less well occupied than they are in the model. And I currently think that is the case here. And another difference map from a cryo-EM, I've forgotten which reconstruction this was. Oh, there it is, 0704, sorry, 0407, I should say. You can see they used, I think it's molecular dynamics to generate these models here, but no matter how much you wiggle around your side chain, you're not getting it to, well, this particular side chain at least, it's not going to flip around into the, probably the preferred rotamer there. But merely peak searching the difference map, as you would do for an X-ray structure, brings this to your attention very readily. And the fix is straightforward. So I've said that using the graphics card, we can now more, what's the word, efficiently generate images. If we're doing an application that runs at 60 frames a second, which is reasonable for a scientific visualization program, you're not trying to head shoot anything, then you have 16.6 milliseconds in order to do things before you must commit to creating a new frame. I have taken one of those milliseconds and spent it doing searching and sorting of the restraints. And the idea is to provide a detailed interactive representation of the high energy components that are contributing to the target function of the geometry. And that is allowing a change of feedback. Whereas previously, we were looking at summary statistics for bonds and angles and planes and so on, using the accept project dialog button. That's no longer useful given the new restraint information that's embedded into the HUD and represented at every frame. It takes about a millisecond. Obviously, it depends on exactly what you're refining, but it's around a millisecond in my timings in order to have a head-up display representation of restraint information. So it looks something like this. We're refining residue at the center of the screen. So first of all, we have balls and dodecahedra, or stellated dodecahedra. And the balls represent the probability of the Ramchandra plot. And the dodecahedra represent, which kind of embedded in the sidechain to some extent, or maybe it represents the probability of the retina. So the idea is that we want to move the representation style to green. So this is as it was in the 0.9 version of Coot. What's new is that at the top there, in the top left-hand side, you can see these multicolored bars actually, because what we want to do is reduce the color of those bars to make them more green-like and smaller. And so they're illness bars really, I suppose. So if we want to adjust the model to make those contributions to the target function reduced, they're interactive, so you can click on them. And if we do so, and we let the refinement proceed, then we can get reduced health bars, illness bars, and the markup has gone green almost across the board. And so we will be happy with that sort of representation. So this is the framework into which I intend to embed other aspects. So instead of floating dialogues for the Ramchandra plot and the sequence view, they will be embedded into the same frame. You can see here there's a tooltip on the health bar there. So if you just mouse over it, it will tell you to which residue, in this case, it's a retina, this block refers. So you can click on it and then adjust the model as needed there. Bottom left-hand side, we can see a mini-map, which part of the protein it is that we're looking at here, or trying to optimize. On the right-hand side, there's a revealer that is providing us with a transparent Ramchandra plot. So you can see that changing as we adjust the model. This doesn't exist today. Lots of the components do exist, but the whole framework of embedding it into, well, the concept of it embedding it into one frame with revealers doesn't exist. It's where I'm going now. So I have a minute or two left. There's a game called City Skylines, and this is part of the, I've been working over the last couple of years with a PhD student called Hamish Todd, and in his previous life, he was a game designer. And so he's been talking to me about games, and one of the games that came to my attention was City Skylines. You can change the environment of any particular city block by placing a school there, or a playground, or a park. And if you do so, the local environment is improved, or people in the environment approve of this. Their status improves, and they let you know that by opaque and then fades away again over a few seconds. So likewise in Coot, you can change a peptide, you can fit a rotamer, you can change a Ramchandra angle, so that the residue at the center of the screen improves, or the one that you're operating on, and the residues in the local environment can feel that change as the minimization occurs. And they can let you know that they approve of that change. The positions of those atoms is no longer compromised by trying to fit against the residue that's incorrectly positioned. So these, likewise, they beam into existence and then they float up as if they're balloons, and then they fade away over a few seconds. Finally, I'm going to finish off with a few virus screenshots, considerations without which any contemporary presentation on methods, developments, and structural biology would be incomplete. So here we go. So this is from Andrew Ward's lab, and it's the next slide as well. So this is a Ebola virus glycoprotein in the news today, or yesterday, something, but quite recent. There's glycoproteins at the center and the antibody fragments bound to it with some symmetry. So the lighting here is not that which you typically associate with Coot. I've done a low pass filter, obviously, for this reconstruction, and you can see that this diffuse lighting and ambient occlusion is bringing out the shape of the protein in a way that was just not apparent or not possible in previous versions of Coot. So we can do map masking. So we can select regions of the map based on atom selections, and that's what I've done here. I've taken the 3 chains of this spike protein, again, Robert Kirchendoffer and Andrew Ward from last year. I've taken their structure and then taken the atom selections and colored it up, and this is a click. There's a button to do this in Coot now. Again, this is an ex-colleague of mine from Oxford, who's moved back to China, published this subtonogram average molecular structure, molecular architecture of the SARS-CoV-2 virus. And this is how it looks in old Coot. If we look at this in new Coot without any change, just read it and it looks like this, which is a considerably improvement in interpretability, I would say. And with a couple of clicks, we can add in additional representation. So I can add radial coloring, and instead of chicken wire, I can change it to a transparent surface. And clay-like material, I can turn up the shininess of that to make it a little more like plastic. And we can get a representation that looks like that with a few clicks. All right, and so with that, I will finish and summarize. The first part of my presentation was about how using a new version of the compiler allowed me to introduce multi-threading, and that has improved several aspects of Coot, most obviously in contouring and also real space refinement. I didn't really mention it in detail, but the validation markup has all been multi-threaded as well. So that makes the interactive clash scores or the clash markup work nicely. So the graphics in Coot have been updated. Well, it's in the process of being updated, really, I suppose. We can better perceive depth and structure. The improved frame rate gives us time to represent details of the refinement. We can additionally add more objects to the scene and represent them with better realism. Martin Noble has provided a library that allows me to fold in ribbon and molecular surface representations. So to finish up, and finally, thank you to Martin for that library. Been useful discussions over the last year or so. Bernard Lohkamp has been and remains the master of Windows. He thinks about Windows that I don't have to. And Hamish Todd has been bringing game-like thinking into my life, and he is the guy responsible for Coot VR. And with that, thank you for your attention. I'll just finish there.
Great, thank you very much. If you have questions, you can send them by chat. I believe you can also raise your hand and we can unmute you. And people can ask questions directly. I'll kick off with a few from chat. If you've got some, raise your hand or send us a chat, and we can unmute you if you like. One, I think, is one that a lot of people have been thinking about. NVIDIA 3D vision system, this goggle-based 3D is going away. Are you going to support it in the 1.0?
1.0, probably not, but 1.1, maybe. I'd like to. I'm not trying to make it go away, but I don't have the system here to test it, so I don't know whether what I'm doing is making it more difficult. I hope not. I mean, I did try to keep in mind that I would be doing this. I think this sort of representation with the shutter stereo, you know what I mean, the NVIDIA stereo would work nicely. Although it may be that because the perception of depth is improved, that you need it less.
Yeah. That's. Yeah. I mean, we don't know how long it's going to be functional or around. I mean, presumably it'll be around as long as Sense 7's around, and then that goes till what, 2024 or something. So after that, who knows?
Okay. Well, it's worth spending a few weeks on it then.
Yeah, exactly. The second question was about compatibility with X-Quartz. I think some people have gotten this X-Quartz issue where they, so it seems like the latest versions of X-Quartz work with Coot, as far as I'm aware. Does that line up with what you've seen?
I haven't been, well, I've been watching the news on whichever mailing list it was, Phoenix, Coot or CP4. There does seem to be a solution with the very latest beta 3.
Yep.
But I should say the Coot version 1.0 runs natively. So X is out of the equation in 1.0, which is nice. Yeah.
So, and that's going to be, you'll be able to be compatible with the new sort of Mac Metal, no GL?
Not initially.
Okay.
And the back end will need to change to from OpenGL to Vulkan, but 90%, probably more, of what I'm needing to do to get OpenGL working is the changes needed for Vulkan 2. It's colored vertices and triangles and buffers, vertex buffers. All of that is going to be the way Vulkan works as well.
It looks fantastic.
So hopefully I won't be doing all this myself, and Stuart McNicholas has been working on, we'll see, CP4MG in Vulkan. I can bring that technology into Coot, fingers crossed, with little effort on my part to make it work. And then there's a layer on the Macintosh that translates Vulkan into metal. So that's the way we're going to make it work on Mac.
One question from Moritz Hunkler, who is here in Boston. The embedded windows in the display now, is it possible to still see those in a floating way? So Ramchandra plot, sequence view, or is the embedded window a sort of singular commitment, like you're one way or the other?
Oh, I see what you mean. Right. Can I pull it out and make it float if I wanted to?
Yeah, exactly. Can I keep my old floating windows if I like them that way?
I will try to make it happen that way. Fingers crossed, it shouldn't be too problematic. But yeah, I'll try to make it optional.
I had a question from Pete Meyer here. Pete, why don't you just go ahead and unmute and ask yours?
Yeah, that may work just as well. So I guess kind of a two-part question. But the main thing is you've talked about Python and scripting, but not a lot about Guile. Does the curl extension library support Guile, or like, is Guile due for a big upgrade in 1.0? Is Guile going away, and I should stop pretending it exists?
Well, it is my preferred scripting language, and if I had to throw one away, it would be throwing away Python. so so
I like it too. You know, it's
I'm attached to it. However, it's been a while since a long time since I've upgraded Guile, and I don't know what's in store for me when I make the change to GTK3 and Guile. I don't know whether that is a 5-minute job or a 5-month job. It's a bit of yeah, unknown.
okay.
Unknown.
Unknowns are, you know, if you got them nailed down, that's good to know. But I guess part of why I was wondering about the extension manager is that I believe that there may be some Coot builds floating around that don't have Guile scripting, and I'm wondering if they try to use the extension manager and they get something, you know, is it going to break? Is it going to yell at you and say you can't do that? Or?
It doesn't, and it should do. It's straightforward for me to just grey out or just not add in that menu item, because the build itself knows it doesn't support Guile. So I can query, as I'm constructing that dialogue, I can query whether it exists Guile supporting, that build supports Guile scripting, and if not, then just don't include those extensions. I'll make a note to do that now.
Thank you.
We had one question about exporting 3D files for electron density maps. Is the new version going to be able to export 3D maps in various formats? Are they listed?
Yes, indeed. So the very first image that I showed you, this one, can you see that you're sharing? This one here, that one has the geometry exported from Coot and rendered in Blender. So I thought that it would be a waste of my time and my skills to try to emulate sophisticated lighting and rendering and ray tracing program inside Coot. So the way to do it is to export it to a program that does do this, which is Blender. And so let me try to remember what the file format is. I think it's OBJ.
Mm-hmm. Yeah, that's what they listed here, OBJ or .ply. Yeah.
Well, okay. I don't have strong feelings. So as well as the model, we can export the map as well. So the way I've been doing it currently as a solid surface, which in Blender you can make transparent. And maybe that's the way to represent structure.
Yeah.
To represent the combination of model and map.
Yeah,
but they are large objects in Blender, and they're not easy to manipulate, especially viruses, which is what I was trying out.
Yeah. So that's.
But yeah, you can do it today. You can export it using, well, the current export format is OBJ, and I may add others.
That sounds great. That sounds like exactly what they were asking for. So perfect. So any other questions? So I had a couple. So don't see any hands up. So for those of you who are on still, if you're not on the Coot mailing list, Paul had a speed run challenge. So speed 1 I think is already through. But if you think your Coot skills are are muscle memory grade Coot skills and not like you really can move quickly, so you can sort of check yourself against there. I think you can pull up the Coot list on Google if you're not on it. But Speed Challenge 2, I didn't see any takers. Have you had any takers on Speed Challenge 2 yet?
No. I think it's a substantial change in the in this skill level. Well, what was curious about the first one was what a range of timings there were. It went from 30 minutes to something like 2 minutes.
Yeah.
And part of the reason why I invented the challenges was that I thought that that Coot's power was not being exploited, and by having a speed run, the way you can just get easy in, easy out, in less time it takes to boil the kettle, you can do all of your model building, go from an R factor of 25% to 16% in the time it takes to make a cup of coffee. That power of Coot wasn't apparent. So that's why I invented the challenge. Now, so what I intend to do is to put a video on, and this is what part of the reason why I was interested in editing videos, where I was going to do the challenge. So it may take me about an hour, maybe 2 hours. And well, actually, I'll probably talk through it, so it won't be at full speed, but it will be a start for speedrunners, or at least a start for structural biologists, and maybe even speedrunners who play games may be challenged by trying to do this structural biology task, because there's loads of them about, and they're playing games, and working on Coot will be actually something that's valuable, I think, socially beneficial to speedrun building virus structures.
Well, that's great. Yeah, I didn't even give it a shot. I know I'm not going to be in the running. It's just, I'm too slow. But I know that. So those of you who are still on, it's, you can Google it. It's on Coot BB, the Coot mailing list. You can, join up on that list too if you're.
It's also on the blog as well. So you do Coot blog and then follow the link to the speedrun. And
you can assess your Coot speedrun skills. With that, Paul, thank you very much. It's great to see all the new features that are coming. I often think about, I do a sort of introduction to molecular modeling and graphics for the, the first year grad students here in the, I think, if we had to build structural biology software like today, and all we had, and we had the computers that we had right now, and the toolkits we have, and the libraries we have, would we have chosen these little sticks? Would we have chosen these little mesh things? Like, is this, so it's, I think that, Chimera X is another great example, like, where you're headed is, sort of the, now we take advantage of like parallelism and, modern GPUs to really do meaningful work and do more work faster. So I think it's great to see.
All right, thank you.
And thank you everybody for joining. Take care.